All right, this is a movie answer key for the first review for AP Physics 2, which is on our electrostatics. So let's get started. This correlates with video 1. How does an object get charged by induction? This is when an object is brought near a charge, but never actually touches it. What charge does a positive object induce on a neutral object? Well, a positive object induces a negative because it causes the electrons to come closer to the side where the positive object is actually near the other object. How does the charge object get charged by conduction? An object is charged when you actually physically touch it and transfer charges across. So for example, what charge does a negative object conduct to a neutral object? A negative conducts a negative charge. Why? Because it gives its electrons or gives a lot of electrons over to the neutral object. Now, of course, if I have a positive object, I will actually conduct a positive charge because the negatives jump across to the positive object when it's touched. How does an object get charged by friction? Electrons are transferred from one place to another, usually by friction overcoming the forces that hold those electrons onto that object. So, and again, remember, charge is actually conserved. What that means is all we're doing is moving charge, okay? So the idea of conservation of charge means the sum of charges within a system is always constant. So remember, we're moving electrons or negative charges. We don't move the protons. They're stuck in the middle of the nucleus of an atom, so they don't move. Okay, let's continue going here. What is the main difference between a charged conductor and a charged insulator? Well, a charged insulator only gets charged locally around one point, where a conductor will evenly distribute the charge throughout because charges actually move easily inside of a conductor. Where does the charge reside on a charged conductor? On the outside surface, okay, of the conductor. Okay, let's move on to video 2. What are the 4 rules for drawing electric field lines? They start on positives and on negatives. They're tangent to the electric force vector. They don't cross. And the number of lines indicates the strength of the field, or is proportional to that field. What are the rules of conductors in electrostatic equilibrium? Charges distribute equally on the outside. Electric field inside is equal to 0, and that's true if there's a hollow space too. And the electric field lines are perpendicular to the outside surface. Okay, let's move on to video 3. What does the value of 1 coulomb actually mean? Well, it's a charge on 6.25 times 10 to the 18th electrons. And 1 electron is 1.6 times 10 to the minus 19 coulombs. What is the sign of the test charge that we use to measure electric field? It's a positive charge. We pretend to put positive test charges in all electric fields and see what actually happens. How do we determine the value of electric force between 2 objects? Well, we use the Coulomb equation. Force electric is K, Q1, Q2 over R squared. And remember, we do absolute value that because we want to assign the direction as plus or minus based on repulsion or attraction. And remembering again that objects of the same charge repel, opposite charges attract. And the Coulomb's constant is 9 times 10 to the 9th. How is determining the electric force on 2 objects similar to calculating gravity force between the objects, which is larger? Well, if you remember, gravity is force gravity equals G m1 m2 over r squared. So it has the same form. Okay. But obviously, electric force is much larger. The K constant is 9 times 10 to the 9th for electricity, but the gravity constant is 6.67 times 10 to the minus 11, which is much smaller. How do we determine the direction of electric force on a vector, on an object? Basically use the concept again that like charges repel, opposites attract, and just draw the vector right on your paper. How do we determine the value and direction of the electric field for a point charge at a specific location? Well, remember, we put a positive test charge at that location, and we see what's supposed to happen to that. If you have a big positive charge that you're measuring, then the positive test charge will get repelled away. It will also be attracted if it's a big negative charge that we're testing. So remember, everything is always drawn from the perspective of a positive test charge. What's the base equation for electric field? Electric field is always force electric per charge and is measured in newtons per coulomb. Okay, for a point charge, that's kq over r squared. And it is indeed a vector when you're done. How do we determine the potential or voltage for a point charge at a specific location? Again, we put a positive test charge at that location. Okay, and then we use the equation volts equals kq over r. Very similar to our electric field, except this one's not a vector. And we did the integral to get the equation voltage equals kq over r. How is it possible to change a change in volts for a point charge to equal 0? It's possible if you do not change the radius, okay, from or the distance from the center of that charge. So if you're going like in a circle around a charge and the radius stays the same, then the potential will be the same everywhere because the equation equals kq over r. How is it possible to get a non-zero change in volts for a point charge and change how far you are away from the center of that charge? So change the radius that you actually are from that charge, because then you would be at two different potentials and there would be a difference. How do we convert the change in potential to change in potential energy? We always take the volts and multiply it by Q. Okay, so electric potential energy is voltage times Q. So that's what we always do to convert. Now remember, potential and voltage means joule per coulomb. So if you multiply that by charge, which is coulombs, you'll be left with joules. What is the relationship between the work done on a charge and the change in potential energy for the charge? The work done on a charge is equal to the change in potential energy for that charge. Now let's take a look at this next question. A positive charge is going closer to a larger charge, positive charge. Is work being done to the electric field or to the charge? Will the charge be moving faster or slower? What is happening to the kinetic energy and electric potential energy? Okay, so if you're moving a positive charge closer to a larger charge, you're doing work to the field, and the charge will be moving slower, and the kinetic energy decreases because you're increasing potential energy. Now, if you're looking at the next case, a positive charge is going farther away from a larger charge. Work is now being done, okay, to the charge. The charge will be moving faster. The kinetic energy will be increasing as electric potential energy decreases. Okay, so in this case, electric potential energy is going to kinetic energy. In the previous example, when you're moving closer to the positive charge, you're doing the opposite. All right, now we're moving on to video 4. What do electric field lines look like for parallel charge plates? Essentially, they're parallel and they go right across, okay, between the plates, and it makes a very constant electric field between the plates. How do you calculate potential difference for parallel plates? Volts is equal to ED. Okay, not like point charges. Since it's a constant E, we just simply multiply the electric field times the distance you go. If there's a potential difference of 6 volts across two charged plates, what's the potential difference if you moved only halfway? Well, that would only be 3 volts. Because you're starting at 6 volts and you're stopping halfway, which would be the 3 volt part. So 6 minus 3 is 3. How do we calculate the change in potential energy for charges moving between two plates? Again, Q times V is electric potential energy. There is a potential difference of 9 volts across two charged plates. What's the change in potential energy of a 4 microcoulomb charge as it moves across the plate from the positive plate to the negative plate? Well, what we're going to do then is we're going to take 4 times 10 to the minus 6 and multiply that by 9, because we're taking Q times the voltage. And that's 3.6 times 10 to the minus 5 joules. Okay? Now it's going from the positive plate to the negative plate. That means the electric field is doing work to the charge. The kinetic energy will be decreasing as electric potential energy decreases. So that EPE there should be a negative 3.6 times 10 to the minus 5 joules from perspective that the field is losing the energy, and that's being converted into kinetic energy. All right. For the Robert Millikan experiment, what is true about the magnitude of the gravity force as compared to the electric force acting on the oil drop? The force of gravity and electric force on the oil drop are equal. What is the base formula for electric field that is used with the Robert Millikan experiment? Electric field is force electric per charge divided by Q. And you can also use electric field is volts divided by distance. You're actually going to end up